to welcome to everybody to a new session, new day of the QCD meets Gravity meeting. So we'll start with a presentation from Thibault Damour from IHES on radiative contributions to gravitational scattering. And Thibault, I will tell you 5 minutes before 40 minutes so that you have only 5 minutes. So.
Okay, thank you. Good. Now it does not work. No. Okay, it works this way. First, let me apologize because when I prepared this talk, I hesitated between giving technical details or explaining mainly conceptual subtleties that we are now facing. So maybe the talk will be disorganized. Anyway, let me first remind people that LIGO Virgo has in the latest catalog has announced the detection of 90 rather secure events, 85 of them being black hole. So we are seeing all the time black hole coalescences, and it is indeed important in view of future improvement in accuracy of detection to improve the methods of describing the dynamics and the gravitational waveform emitted by coalescing black holes. Let me also remind you that on the example of the first detected binary black hole coalescence, which is still one of the highest signal to noise ratio, that here, yes, I should have. Do you see my pointer here?
Yeah,
very good. Yes. Okay. So these are the raw data from the Hanford detector, and the wave you see, which is really the amplitude fractional change in the length of one of the arms of the interferometer at Hanford. They fluctuate, but it's not at all the gravitational wave. This fluctuation is at the level of 10⁻18. So this is broadband noise. And the gravitational wave signal is about 1,000 times smaller at the 10⁻21 level. So it is totally lost in this thing. And among the various methods, although there are also methods that do not use templates, but if you want to extract information from these gravitational waves and be sure you have detected them, it is quite important to have a bank of template waveforms. And the effective one-body approach to complete gravitational waveforms, including the merger and the post-merger, the ring down, is still one of the prime tools to do that and to be able to deduce data from the observations. Now, in principle, the problem is the following. This is the explicit form of Einstein's equations in harmonic coordinates. So we want to solve Einstein equations actually in vacuum when discussing two black holes for a space-time which represents the motion of two black holes in space-time, the emission of gravitational waves all the time, the dynamics being gravitational wave radiation reacted due to the radiation damping, and the merger, and actually what you really want is the waveform emitted at infinity. Now, just a few words to remind you that the effective one-body approach was actually historically rooted in quantum mechanical work of Brezin, Itzikson, Zinn, Justin, that was emphasizing that one could get information about bound states of positronium from resummation of aconal scattering amplitude. And this suggested an approach in which one would replace the perturbative knowledge of the two-body conservative dynamics for the conservative dynamics part by a description of an effective particle of mass mu, the effective mass, moving in some external space-time metric, a dynamical metric, which has nothing to do with the metric in space-time. And this means that if it were a geodesic motion, you would have a simple mass shell constraint, just quadratic in P. And then it was found that you need to go beyond geodesic motion. You need Finslerian corrections, that is to say, terms in this mass shell condition which are higher order in momenta. Then already at the beginning, the idea, quantum mechanical ideas were useful in the sense that if you want to map a real problem in an effective problem, thinking in terms of quantized quantities in both problems allowed to solve what was to be solved, and then to find that the energy in the effective problem was linear in the square of the energy of the real problem. Now, from the practical point of view, the effective one-body method combines two things: a knowledge about a conservative dynamics, and Hamiltonian describing conservative dynamics, but you add to it a radiation reaction force. This radiation reaction force is computed in terms of a resummed waveform, actually, and then combining the two gives a radiation reactor dynamics, which is represented here, and at the same time you compute the full waveform not only during the in-spiral, but also the last orbit, the merger, and the ring down after the merger. Okay. Now, yes, so this busy slide contains some of the central messages I want to discuss, which is the fact that when you look at the dynamics of two bodies in general relativity in some gauge, and for clarity, you expand it in both in the Newton's constant, and which means really the dimensionless parameter gm over c square b, where b is then impact parameter or a typical distance between the two bodies. And also you expand it in v square over c square, which is represented here as just 1 over c square. Then you have terms which are first order in Newton's constant, which are called also one post-Minkowskian, okay? Although they are, the one here is Newtonian. Evidently, the Newtonian term would be this one here. Then at the 1 p.m. level, you have an infinite sequence of v square over c square corrections. Here I have written the thing only up to the 5 p.m., 1 over c10. Now at the 1 p.m. level, when you write things in the simplest way, this contribution is purely, contains only even powers of v over c, and traditionally something which is even powers of 1 over c in post-Newtonian language is called time even, because changing t minus t changes velocities in the opposite of velocities. Now, at the second post-Minkowskian level, g square, the first two terms, like the 1 over c square would be a one post-Newtonian correction, first post-Newtonian correction. You have the second post-Newtonian correction. And then at the 1 over c5 level, which is called 2.5 pn, you start seeing terms which are odd in v over c, or in retardation also, actually. And all the terms odd in 1 over c are here put in red, because traditionally, these terms which are red are thought as being dissipative, okay? And this is true for the terms here, 1 over c square, 1 over c7, 1 over c9. Also at the g cube level, this is true for the 1 over c5, 1 over c7, 1 over c9. It remains true at the g4 level if you look at the 1 over c7 level, but then something happens which is indicated by the blue color here, which is that starting at the G4 level, or 4 p.m. order, and at the 4 p.n. level, which means 1 over C8, then at this level, this term and this term actually are a mixture of being time even and time odd, but still, this is okay in the sense that, as we will discuss later, this mixture of time even and time odd can be uniquely separated in something time even and something time odd, and the time even is shown to be conservative, that is to say, to correspond to an Hamiltonian. Okay, but now we have reached, sorry, will I be able to go back? Yes, okay, from here. Now, but now recently, one has reached the next level, which is the 5pn level, or 1/C10. And some of the 1/C10 level at lower post-Minkowski orders are not dangerous. But starting at the G4 level, actually, this term, so G4/C10, becomes quite delicate. Similarly, also the terms 5pn in the G5 and the G6. And there will be further talks about that today. But there are several types of ambiguities that mean that at this level, there is no well-defined way today to separate these terms in conservative and radiation reaction types, especially for a simple reason, but this is not the main reason. In addition to the fact that we will explain why there are ambiguities, a term like G4/C10 is just mechanically at the level of the square of the term G²/C5, which is the leading order radiation reaction, which means that terms that come from the iteration of radiation reaction come at the same level as this. Okay, so this is like the main conceptual introduction of what I will talk about. Now, so let's discuss within the various approaches to the binary dynamics, how one can try to separate the dynamics in conservative and radiation reaction, because it is technically useful. And one of the main messages of this, by the way, busy slide that I will discuss in detail is, I think there is an ambiguity in the literature, is that many people use the word, we compute the conservative dynamics, it is the conservative dynamics, but they mean different things actually by conservative, or at least they mean different ways of defining the conservative dynamics, and the ambiguity now I think is becoming serious and important to resolve. So within the post-Minkowskian approach, I will start by reminding you that actually one does not need, in principle, to distinguish, to separate the dynamics in conservative and radiation reaction. That if you compute the equations of motion, here, this is sketched here. If you have the theory of two classical world lines, massive world lines interacting by gravity, you can write successive approximations to the equations of motion, let's say, of the first world line, computed from the effect of both the first and the second world line. And these equations of motion, they will contain everything you want, and then you can compute the scattering from this, and you never need to say a priori that this contains radiation reaction and conservative effects. Okay, I will discuss this in more detail, but let me say that within the ADM approach, there is a specific way of separating conservative and radiation reaction effects, which the ADM Arnovit-Deser-Misner approach consists in solving the constraints of Einstein's theory, but in a gauge, a Coulomb type gauge, where some of the degrees of freedom are still the gravitational waves, and then you need to say what you do when you eliminate these gravitational wave degrees of freedom. I will discuss also quickly how in the Fokker-Wheeler-Feynman approach, you can define a conservative dynamics. And okay, let me proceed instead of discussing too much on this slide. Now, indeed, so the first point is when you iterate the equations of motion of two world lines in the classical way of solving Einstein equations, either to compute bound systems or scattering, like here, you and this was an approach which was introduced at the end of the 70s and the 80s to resolve the problem of whether the observed binary pulsar motion by Hulse and Taylor was in agreement with general relativity. Then you must and you can use retarded propagators at each stage of the iteration. When you do that, you get equations of motion, which are here written, and they were computed at the time up to the 2.5 PN order. And then you get these full equations of motion, and then you prove that up to 2 PN, they derive from an acceleration-dependent Lagrangian. So this part is really conservative. And then you have an extra part, which is by definition dissipative in the sense that it does not derive from an action. And what I want to emphasize is that this leading radiation reaction term force contains G square over C5. So you see the G square here, the C5 is in the index. And because there is an extra G, G cube over C5. And at the time, it was noticed in collaboration with Nathalie Derriel that there are radiation reaction effects at the G square level. And you see them in small angle gravitational scattering. And you see them via the fact that the mechanical angular momentum of the system defined explicitly from the 2 point particles is disappears because of the equations of motion, I mean, is lost, and that this loss of angular momentum agrees with the standard DeWitt Thorne formulas for the flux of angular momentum emitted at infinity in the form of gravitational waves, okay? And let me just mention in passing that Di Vecchia and Gabriele Veneziano and with Wilkowski have emphasized that it is somewhat paradoxical when you think from the quantum mechanical point of view to have a loss of angular momentum at a lower order than the loss of energy, and that this is linked with subtleties with the BMS and the structure, BMS group and structure of gravitational waves at infinity. Now, let me just say quickly that in the Arnovit-Deser-Misner approach, you use, this is the Coulomb type gauge you use. And then if you want to find a conservative Hamiltonian, you solve the equation for the gravitational wave degrees of freedom, which are part of the dynamics here, HTT, transverse traceless, by using the iterated time symmetric Green's function when you solve this. And you can do that, and this was done up to the 4 PN level. So let me stop this. And the only problem is that this leads to infrared divergences at 4 PN, but they have been completely resolved by using SelfForce matching. Let me also mention quickly that if you don't want to have the reduced conservative dynamics, but the radiation reacted dynamics, as has been shown explicitly by Jankowski and Schaefer, you can work with double variables within the ADM approach. Now, let me mention that a generalization of the Fokker-Wheeler-Feynman electromagnetic conservative action at a distance was explicitly exposed by Esposito Fares and myself long ago. And the idea is that if you integrate out from the point particle Einstein, Hilbert, and gauge fixing action, you integrate out the gravitational degrees of freedom by solving iteratively Einstein equation in presence of two world lines, by using at each step a time symmetric Green function, then formally this defines a conservative action. And this is important because in when later I will discuss from the TuttiFrutti point of view, the conservative action having some properties, one was assuming that there is this conservative action, and because of its construction, it is polynomial in the two masses. Let me quickly say that other ways in the literature which are quite important in separating conservative and radiation reaction effects, especially as studied by Ayer and Will, but this was the long predecessors, is to write balance equation saying that if you have a conservative dynamics and you add to the conservative dynamics a radiation reaction force, this means that the energy, angular momentum, and other conserved quantities of the binary system will be change, will be damped because of the radiation reaction force, and you want to equate the losses of mechanical energy and angular momentum of the system to the fluxes via gravitational waves at infinity of energy and angular momentum modulo some so-called short terms. And this is an efficient way of computing radiation reaction, which is used in EUB construction. Now, let me also mention that the EFT approach, started by Goldberger, Rothstein, and others, where how in this approach, one is trying to separate, by separating the scales of the binary system and the radiative modes on the long wavelength, one is supposed to integrate out the potential graviton modes to leave a theory of interaction of a system which then at the end, after integrating the graviton modes, is described by multiple moments interacting with the long wavelength radiative modes. And this plays an important role in the recent work of Forfas-Tourani and Blumlein. Now, for many years, there was a happy marriage between post-Newtonian, post-Minkowskian, and everybody else. But something subtle happened when it was understood a long time ago that that there must be, in a sense, a fundamental breakdown of the usual 4pn way of approaching the dynamics at the 4pn level, because there are effects that you can see in the near zone, and this is the explicit calculation at the time, saying the near zone metric acting on the binary system contains a term which comes from tail effects, and which means that a very, let's say, a soft, nearly radiative, a radiative graviton mode was emitted long time in the past, was backscattered on the curvature of space-time generated by the total mass energy of the system, and backscattered back on the system. And this creates forces in the motion of the binary system, which are time disymmetric. They are neither time even nor time odd, but still at this 4pn level, they are uniquely decomposable in time odd and time even. And then the time symmetric part can be described by...
ladies and gentlemen.
Sorry. You fine? Maybe mute everybody.
Can you mute yourself?
Okay, so this so at the 4pn level, this gives rise to an explicit...
Just 1 second, Thibault. I don't have the right to actually...
Yeah, everybody, and then just...
No, I can, but I'm host, I can't mute them.
Okay, please continue.
So at the 4pn level, this gives an explicit term in the Hamiltonian, which is non-local in time, which is at time t, it's an integral over all the other time t primes. And if you want the conservative things, you need to integrate both on the past and on the future, so that it is really an action. Because it has a logarithmic divergence at v equals 0, when you do this, when this was done at the beginning, there was just an ambiguity of one constant in regularizing this log. And this constant was first determined, oops. Now my slides disappeared. Keynote quit experience. Okay, reopen, just a moment, sorry.
You went out from the share screening actually. Can you share screen again, Thibault?
Okay, I will. Yes. It disappeared. Yes. Oops. Not that. Okay. Oh la la.
We are
Just-
seeing the Mathematica notebook, yes.
You can see what I'm doing also. Something else. Okay, Zoom. Where is Zoom? No, but here it says that I'm screen sharing. So it's
Yeah,
not
but you are screen sharing another window, not the one of the
Yes.
presentation. Maybe you want to go out from the share screen in the moment at the end.
Yes, you're right. Okay. And now I should go to be sure I am on the good. Yeah, I was on the good. Just a moment. Yes, sorry.
That's fine. We have a coffee break afterwards.
That's okay. It's a Zoom era. We're used to this. Don't worry.
Yes, because yes, usually I don't use several windows. So, because Zoom went on the wrong thing also. It went on the second screen. And I have to find again. How do you find the first screen?
Well, I would suggest, unfortunately, that I think it's better if other people have a better idea, but I think you should go out from Zoom at the end.
Yes. Let me do that. Sorry.
Yeah, that's fine.
Okay.
I think he's back.
Is he back?
Yeah, he's back. He's co-host.
Okay, great.
Great. We see your slides.
Okay. Who are you there? We don't hear you if you are talking.
It says
Uh,
join
Thibault,
audio.
we don't hear you. If
He was muted. I
Oh,
asked
that's
him
right.
to unmute.
Do you hear me now?
Yes.
we can hear you. We don't see you, but doesn't matter. So please
Yes.
continue.
Okay. Now, yes. So, yes, I don't need this. So let me explain conceptually SelfForce, how SelfForce was used in gravity in many different ways. So what is SelfForce? SelfForce means one loop in a black hole background. So you are considering a binary system where there is a large mass, M2, which is the mass of the central black hole, and a small mass, M1. And the small mass, M1, is moving in the background of the black hole generated by M2. And you consider effects which are one loop, which means in the effective action, which are second order in the small mass M1. If you expand the black hole background in perturbation theory around flat space, this means that you consider diagrams of this type where you still have one loop that closes on M1, but many external vertices of many types. A lot of work was done. There is a very efficient technology going back to Ray J. Wheeler-Zerilli. And then it allows to compute things. In particular, it was found by Letiègue, Blanchet, Whiting, and collaborators, including Alessandra, that there is a convenient way of connecting things you can compute from SelfForce computations and the Hamiltonian of the terms in the Hamiltonian which are quadratic, let's say, in M1. And essentially what I want to say here is, as it has been shown by Fujita et al., this thing essentially says that you use the regularized symmetric Green's function again. So it is a Fokker action, but it is a Fokker action for the Green's function of this word line within the black hole background. Okay, and this is used a lot. Actually, I thought I had deleted this slide. Now let me explain quickly that among the approaches that have been developed recently, there is the so-called TuttiFrutti approach. TuttiFrutti because it combines many different tools, post-Newtonian, post-Minkowskian, multipolar post-Minkowskian, etc., etc. But what I want to emphasize is essentially the two important tools is to use the first law, which means that you use something from the symmetric Green's function computed Fokker action in an external background, okay? And then you use polynomiality in the masses to determine many terms which are nonlinear in the symmetric mass ratio from what is determined from SelfForce. SelfForce gives you terms which in the Hamiltonian per divided by the effective mass mu, so it's not the full Hamiltonian, I mean, it's the full Hamiltonian, but scaled by the mass of the mu, then the terms linear in nu are computed from SelfForce. And this allows to compute most of the terms in the Hamiltonian at 5pn and 6pn. For instance, at 5pn, you determine everything except two undetermined parameters. I want, so it's an older version of this thing. Let us see how bad it is. Maybe because this thing disappeared on a different screen. Anyway, so the non-local terms in the action, which starts at 4pn and then go at 5pn and 6pn, are explicitly written as logarithmically divergent integrals, okay? And they contain fluxes of gravitational waves, and then you use SelfForce to complete them. What I want to emphasize is when using the assumptions that I've made before, that is to say, we are talking about a conservative dynamics which satisfies polynomiality in the masses, then this allows to determine in principle all the terms at the 4pm level, I mean up to the 4pm level included, G4, and we did it explicitly for some terms I will mention. Yes, so I absolutely need to find again now my other, sorry, this is not the good presentation because I had updated it. Yes, sorry. Okay. Okay. Do I need to stop share screen? Okay, let us see if it works.
Actually, you already went out from the sharing. You may need to re-enter the sharing now.
I have to stop sharing?
No, you already stopped sharing.
Sorry. Okay. So.
Okay, let's see if we'll see the slide.
Okay. Yes, so I have to find a good one. Yes. Let me then, okay, let me see, share screen. Yes, now play.
Okay.
Okay. Now it should be the good one. I've made modifications. Yes. Okay. Now, yes. So I already said this. Now the point I want to say, in a recent work with Donato Bini and Andrea Geralico, we used results from this TuttiFrutti approach to complete the recent computation by Zvi and his collaborators of the potential graviton contribution at the G4 level. And we are looking forward to the talk soon, whether they will present new results. But we computed from TuttiFrutti, that is to say, from the scattering angle computed at G4 level and at the 6 PN, what would be the conservative radiation graviton contribution. So we use the scattering angle and this result to compute an explicit contribution that goes up to the 6 PN level now. But this was for the G4 level and the 6 PN level. Now, at the next post-Minkowskian levels, G5 and G6, but staying at the 5 PN level, now there is frontier work which has been done to use the EFT approach to binary dynamics, first by Forfaz-Tourani and recently breakthrough work by Blumlein and collaborators, who computed not only the potential graviton, but also they estimated the effects of the radiation graviton mode. So conservative effects due in principle to the exchange of the graviton nearly on the mass shell interacting with the quadrupole moment and the angular momentum or the quadrupole moment cube. Okay, so from these results, one can determine the two missing coefficients at 5 PN, d bar 5 and A6, as linear combinations of the terms in the effective action which are supposed to describe these interactions. So these are supposed to be conservative contribution to the Hamiltonian X, but due to radiation graviton long-range interactions written as explicit products of time derivative of the quadrupole moments and the angular momentum of the system. So let me mention that we recently noticed that there was a coding error in the way we had defined the sign. That is to say, we initially intended to define the sign of this action in the same way as Forfaz-Tourani with a plus, but actually in the code, what was used was a minus sign, which means that all the formula we wrote were, I mean, most of the formula were correct, but we need to interpret them in terms of this minus sign. But what is important here, so for instance, if you knew these three coefficients, so there are three unknown rational coefficients that appear here, which are in principle computable from these diagrams. And from the knowledge of these coefficients, you can then compute the rational terms here. But the important point is we derive from the scattering results of the TuttiFrutti, we derive a constraint that these three rational coefficients must satisfy, okay? And this constraint is a consequence of all the hypotheses of our work, and it is here, okay? When you insert in this constraint, the result computed by Forfaz-Tourani, the constraint is not satisfied. Recently, Blumlein and collaborators have computed new values for these coefficients, but still they do not satisfy this, okay? They express it in saying they want to change some other terms, but actually what it means is that these coefficients do not satisfy this constraint. So
okay, you have 4 minutes.
Yes, good. So here we have seen above that there is a tail of which involves many Green's functions. That is to say, are we talking about radiation reacted dynamics from the beginning? If one was doing this using in a classical computation and in a quantum one, the Feynman Green's function, would would give the correct answer from the beginning to the end. But it is convenient to define conservative action. I should say that Fofa and Storani actually advocate a different way. And I should say also that it is totally unclear to me what Blumlein and collaborators do. I have asked them questions about exactly what is the link between what they compute in their appendices and their work, and I never got an answer, so I hope we will get some answers. And then there is the issue of terms quadratic in radiation reaction, because now if I, yes, this was my thing. Now, I will be fast, I have just a few slides more. Now, up to now, I have been talking essentially about conservative dynamics, where in the Wheeler-Feynman sense, you think that there is as much incoming radiation as outgoing radiation, so the system does not lose energy. If you consider the radiation reactor dynamics, where the system loses actually energy and angular momentum, you want to compute the effect on scattering of this, okay? And I will not discuss in detail the fact that it has been shown recently in work by Divekya and collaborators, by myself and then others, that taking into account radiation reaction effects at order G cube, resolve the puzzle between an apparent discrepancy between the energy limit of the work of Amati, Ciafaloni, Veneziano, and at G cube, and the recent result of Zibern and collaborators at G cube. Let me just recall that the computation is very simple, actually. It consists in adding a term, radiation reactor contribution to the scattering angle, relative scattering angle, which is linear in energy and angular momentum loss, and which can be computed in just 2 lines, and then which resolves the discrepancy. Let me finish by saying that in our recent paper with Donato Bini and Andrea Geralico, we extended our previous work by computing the full effect on the change of the impulse of the 2 particles, P1 and P2, of the effect not only of energy and angular momentum losses in the incoming center of mass frame, but also of momentum loss, I mean of recoil. And then we could derive, we could rederive a result which has been derived by Herman and collaborators using the Kosover, maybe O'Connell amplitude approach. Okay, so which means that at this level, all our results give radiation reaction effects in the scattering of 2 bodies, including effects at 1/C5, 1/C7, 1/C8, and 1/C9. But we stopped at this level because we emphasize that, as I said before, at the 1/C10 level, 5pn level, there are terms square in the radiation reaction, which are difficult to describe. They cannot be described by a linear approach in radiation reaction. So one needs to think from scratch. Let me also remind everybody that although the amplitude approach to scattering has done extremely important and beautiful results, one has to keep in mind that the domain of validity of the quantum Born-Feynman expansion is the opposite of the domain of validity of the classical scattering. I mean, the analog of the fine structure constant, like this quantity, must be very large in the classical computation, why it must be small in the quantum computation, except if you really prove in detail that you have exponentiation, Econal-like exponentiation. So anyway, this shows that the current level of G4 scattering will put to the test all these interesting conceptual advances. Just to conclude, evidently, I should have emphasized it more. It is true that it is important to improve our knowledge of the dynamics of 2 bodies, and the scattering approach is very useful. But the point is that when taking into account radiation-related effects, there are discrepancies, and now there are discrepancies between 3 different papers at the 5pn level. And these discrepancies must be resolved because it would be very good to know the 5PN dynamics exactly. So just to say, like Henri Poincaré said, there are no problems which are definitely solved, and the GR binary problem is of this type. It is only more or less solved. Okay, thank you.
Okay, thank you very much, Thibault.
Yes.
So we now take questions. You can write the question in the chat, or people who are locally there, I guess they will come close to the microphone. So we are 5 minutes late, but there were these interruptions, so I would take just 5 minutes now. If you, I see Zvi saying yes. So are there questions?
Maybe I can ask one. So could you comment more on the subtlety of radiation reaction square terms?
Okay, so from one point of view, there is no subtlety at all. That is to say, am I still sharing screen?
Yeah, you are.
Yes. That is to say, if one was using, let's say, yes, if you use, for instance, a classical approach, you compute the equations of motion using retarded Green's function from the beginning to the end, and you compute the post-Minkowskian or post-Newtonian, whatever equations of motion, then, okay, then you just need to integrate. So there are equations of this type. Then you ask, what is the scattering that you derive from these equations of motion? And in computing the scattering, there will be terms that will come from iterating this term. The only subtlety is that these terms are gauge dependent. That is to say, you cannot say universally the terms coming from the square of the radiation reaction is equal to this, because it depends on the gauge you use, okay? But the subtlety comes if you are using an approach where you have something that you call conservative dynamics, and then you say, I want to complete this conservative, for instance, define using a time symmetric Green function from the beginning to the end, and you say, I want to add to this conservative dynamics a radiation reaction, then you have to compute what is this radiation reaction with sufficient accuracy to be sure that it contains the effects that would come from the square of the radiation reaction in the other approach. So if we knew everything in detail, there would be no conceptual subtlety. It's just that at this technical level, there is a subtlety. Gabriele has raised his hand.
Yeah, Gabriele has a question.
Yes, yes. Hi, Thibault. Just, I was wondering about this radiation reaction terms at 2 p.m. level. Can you explain a little bit more their origin?
At 2 p.m.?
Yeah, you wrote 2 p.m. level.
2 p.m. Yes.
You have a string of C.
Yes, sure.
Terms. Yeah.
So I did not put so.
What
okay.
is the physical meaning of those terms?
The physical meaning.
Because
so,
I don't see a linear response to radiation in that case, at that order. At order G cube, yes, but at order G square, I don't understand. I didn't remember actually that they are there, but
yes,
I'm sure.
I was myself confused. Okay, no. These terms, by the way, are responsible for the G cube scattering angle. Okay, so
okay.
Yes.
Oh, you are not talking about the scattering angle.
Exactly. I'm saying
in the scattering angle there are no such terms.
Exactly. They are in the equations of motion. So they are
okay. Not in some physical observable.
No, let us say. Not.
Okay.
Sorry.
Thank you.
Okay, thank you. Any other question? Brief question or comment? Okay, if not, let's thank. Sorry. Yes.
So I want to ask, because since we
believe that now the 3 p.m. dynamics is solved. We do have a Hamiltonian, but as far as I can tell, no one has written kind of the PN version of the radiation reaction forces. So do you have any idea of how this can be extracted from what we already know?
At the G cube level.
The G cube level, yes.
The problem is that the radiation reaction, I mean, in the equations of motion, I mean, if we talk about Hamiltonian, we are at the level of equations of motion, let us say, then the radiation reaction starts at G square. So indeed, we are thinking about this explicitly, but there will be a sum of a term at G square, which is contained actually a radiation reaction at G square level, which is implicitly contained in my old work with Louise Bell, Nathalie Derriel, and collaborators. But I'm not sure, indeed, today from the known results, whether one can immediately write the full G square plus G cube radiation reaction. It's a good question, yes.
Thanks.
Okay, again, thank you, Thibault. Let's thank Thibault for the very interesting talk. And we now have a presentation by Peter Markard from Daisy Zoiden in Berlin. And do you want to share your screen?
Yes, let me share my screen. Interesting.
Yeah, we don't see yet.
Yeah, interesting was referring to it doesn't work.
You mean you are not allowed, or?
No. Ah, there we are.
Yeah.
Now we just need to get this bigger.
Mm-hmm.
So no.
We do see something, but actually there's not like slides. It's just a gray blue screen, kind of.
Okay.
So maybe
Let me stop this again. Sorry.
Yeah, no, that's fine.
I don't know. Maybe it was again a newer version. I don't know. It's always kind of a miracle if it works or not.
Open. Anyway.
Okay. Let me suggest maybe we can we swap the talks and have Simon after me first?
Yeah, I think there
The
is
speaker
no
went out to the bathroom.
Okay. Then
yeah.
Just try for 5 minutes and then we can swap if necessary.
Okay, let's see why this doesn't work.
We can be relaxed.
You can also try to do the share of the entire screen, you know, not just one file. So that then
yeah. This doesn't give me anything. Okay, this worked a couple of days before. Great.
But what do you see when you try to share the screen?
It tells me I can share it the basic screen, and that's empty. So there's nothing I can. Okay, let me just disconnect and connect again. Maybe this solves the problem.
That's a good idea. And what about Shen? Is he back in the room, or?
Yes, I'm back.
Okay, give me 1 minute to reconnect, and then if it works, I give my talk, and otherwise we swap it. Okay. Just 1 minute.
Okay, so then let's wait a moment that he comes back.
Still trouble. Yeah, maybe we should swap that.
Wait for 1 minute. Okay.
We are waiting just 1 minute to see whether he's back and it will work.
Okay, we're in California, we should be relaxed.
That's fine. Yeah, it doesn't seem to come back actually.
Could you get me the co-host rights again, please?
Yeah, can someone give? No, you are co-host, Peter. You are co-host.
Okay, now I'm co-host again.
Mhm.
Okay, okay. Let's swap the talks. This doesn't work.
You still have the problem. Okay.
I still have the problem. Sorry for that.
No, that's fine. So let's have now Shan Shan from University of California in San Diego, and he's going to talk about tail effects in binary scattering. He's giving the presentation from locally, so but we should see it appearing on the Zoom.
It just takes a minute to set up.
Okay. Okay, so I will tell you 5 minutes before you have 25 plus 5, and I will tell you 25 minutes before.